proof we just looked at, it may have felt like a lot, but the theorem that we proved with it gives us a way to orthogonally decompose any vector. So let's take a look at an example. So let's let W be a subspace of R3, and let's let W have the orthogonal basis B with these two vectors. All right. Let's let X be vector -3, -3, 2. We want to orthogonally decompose vector X with respect to subspace W by finding vectors W and W perp, where vector W is in subspace W, and vector W perp is in subspace W perp, the orthogonal complement of subspace W, such that X is equal to W plus W perp. Okay, so in other words, we want to apply the theorem we just proved. Now, according to the theorem, we know that we can't do this. We know we can do this. There exists a vector W in subspace W. There for certain exists a vector W perp in subspace W perp, so that this is true. Okay, and we know that the way we can do this is unique. There's only one way to do it. Now, we demonstrated how to do this in the proof. Vector W that's going to work here is going to be the projection of vector X onto subspace W. If we can find that, we find this vector. And if we can find this vector, W perp's real easy. Because once we find vector W perp is just going to be vector X, which we know, minus vector W, which we can find. Okay? So we're going to start by finding vector W. To find the projection of a vector onto a subspace, we need an orthogonal basis. Fortunately, the problem gives us one. Vector or basis B is already an orthogonal basis. Okay? And so all I'm going to do is I'm going to take the dot product of vector X with the first vector here. I'm going to call the first vector F1. I'm going to call the second vector F2. So let's find the projection onto vector F1 first. So this is the formula for the projection of X onto F1. And then I add that to the projection of vector X onto vector F2. Okay. In this case, that's the only two vectors in the basis. So this will give me the projection of vector X onto the subspace W. All right. So let's do the arithmetic. Start with the dot product of X with F1. I'm going to do it kind of quick. If I take the dot product of these, I will get 12 plus 6, that's 18, plus 4, that's 22. So the numerator is going to be 22. I'm going to divide by the norm of F1 squared. So that's going to be -4 squared is 16, plus -2 squared is 4. So it's 16 plus 4 is 20. Plus 2 squared, that's another 4, that's 24. Okay. The norm means it's under a square root, but then I square it, so the square root goes away. So I get 22 over 24 times vector F1. And vector F1 was -4, -2, 2. And now let's do the same thing for projecting onto vector F2. So the first thing I need is the dot product of vector X with vector F2. So if I take the dot product, first term times first term, I get 3 plus -6. So 3 plus -6 is -3. Plus 0, that means I stay at -3. So I get -3 over norm of F2 squared. So that's 1 plus 4 plus 0, that's going to be 5. So negative 3/5 times vector f2. Vector f2 is negative 1, 2, 0. Okay, let's do the addition. Let's simplify to the extent that we can. 22 over 24, that's 11 over 12. Do the scalar multiplication. 11/12 times negative 4. Notice I can reduce. I'm going to get negative 22 over 6. Well, I can reduce further than that, can't I? 4 goes into 12 3 times, so I'm going to get negative 11 over 3. Okay, and then 11/12 times negative 2 is negative 11 over 6. And 11/12 times 2 is positive 11 over 6. Plus negative 3/5 times negative 1 is going to be positive 3/5. Negative 3/5 times 2 is going to be negative 6/5. And negative 3/5 times 0 is 0. Let's do a little fraction arithmetic. I need to add the two vectors, and I've got some fractions. So negative 11/3 plus 3/5. Least common denominator is going to be 15. Negative 11/3 is going to be negative 55/15. 3/5 is 9/15. Negative 55/15 plus 9/15 is going to be negative 46/15. Next one, negative 11/6, negative 6/5. Least common denominator will be 30. Negative 11/6 is negative 55/30. Negative 6/5 is going to be negative 36/30. If I add those together, I get, what, negative 91/30? And then finally, 11/6 plus 0 is 11/6. Okay, so we have our first vector. We need to define W and W perp. We have vector W. Okay, now we need to find vector W perp. Vector W was the hard part. Remember, we want x to be equal to vector W minus W perp. So that means, I'm sorry, plus W perp, plus W perp. So that means vector W perp is going to be vector x minus vector W. Okay, I know vector x and I just found vector W, so I can find that W perp. Vector x, what was it? Negative 3, negative 3, 2. And I'm going to subtract vector W, which is negative 46/15, negative 91/30, and 11/6. So I'm going to need common denominators again. Negative 3 is negative 45/15. So negative 45/15 minus negative 46/15. That's going to give me a positive 1/15. Same thing here. I'm going to need a common denominator of negative 30. Negative 3 becomes negative 90 over 30. Negative 90 over 30 minus negative 91 over 30ths. That becomes positive 1 over 30. And then 2 is the same as 12 sixteenths. 12 sixteenths minus 11 sixteenths. I'm sorry, 12 sixths. 12 sixths minus 11 sixths is 1/6. And that's the other answer. Okay, so I have my two vectors. W is in subspace W, W perp is in subspace W perp. W is going to be orthogonal to every vector in W perp. Vector W perp is going to be orthogonal to every vector in subspace W, including each other, by the way. You could take the dot product of vector W perp. You will see that the dot product of these two vectors will be 0. They are orthogonal to each other. And if you add these two vectors together, you will get vector x back. We have found the orthogonal decomposition of vector x.